Hello everyone, I'm Xie Pengfei, a postgraduate at Information Engineering University from China, Zhengzhou. Our work's title is Improving the Transferability of Adversarial Examples with New Interaction Framework and Input Dropout. Let's start our presentation. In recent years, deep neural networks have begun to shine. It has achieved good results in tasks such as image classification. However, deep neural networks are not safe. Seasoning first proposed adversarial examples, which look similar from the original examples but make DNNs wrong. As you can see, the pattern with the adversarial noise looks like the original pattern, but it can be misclassified as given by neural networks. In fact, adversarial example problem can be summarized as shown in the red box. The purpose is to make the noise value of the adversarial example and the original label larger, which will cause the neural networks make mistakes. The attack methods for generating adversarial examples can be divided into methods based on optimization, gradient interaction, and generation model. Among them, gradient-based attack methods are the most popular due to their fast generation speed and low algorithm complexity and good transferability. As the picture shows, transferability means that adversarial examples generated in substituted models can also attack other models. Our work is to improve the transferability of adversarial examples. Before we introduce our work, I give a brief introduction to the existing excellent work based on transfer-based attacks. I divide them into two categories. One is to use gradient information to prevent overfitting, and the other is to improve transferability through data enhancement. In previous work, step size alpha, interaction times t, and maximum permutation epsilon often satisfy the center relationship to avoid gradient overflow. In fact, this traditional framework does not perform all the attack performance of algorithm. Zone proposed the region fitting, which expands the interaction step size alpha to epsilon, but its iteration times are still limited. In fact, we can regard the gradient descent as a spear and the cliff as a shield. The gradient descent leads to the increase of loss, while the cliff limits the disturbance to reduce loss, and the two are in a gain state. We directly select a large step size to prevent overfitting, and then extend the number of iterations to improve attack performance. We will not gradient overflow because in a certain iteration run, the benefit of extending the iteration run is greater than the loss of attack performance caused by clip. So we propose a new framework to develop the real performance of the algorithm. Our formula is shown in the figure. We also show the relationship between our framework and the previous iteration methods. We conduct experiments on the imagined dataset used in the competition of NIPS 2017. We selected 10 models for experiments, including 4 formal training models, 3 ensemble adversarial training models, and 3 more robust default models. We attack a single model in step 3, and then test it on other defenseless models and 3 ensemble adversarially trained models. Compared with 10 iterations, the attack success rate of 50 iterations with different step size increases by an average of 6.9% on the defenseless model. We attack 4 defenseless models in a sample manner and test them on 6 defense models. In our framework, we increase DITIMIM by an average of 14.5% on the ensemble adversarial training model and 2.6% on the denoise model. But as we continue to expand the iterations to 200, we find that the small steps are prone to overfitting. To prevent overfitting, we use dropout in the data layer. We verify that dropout also has invariance. When the dropout rate is between 0 to 0.5, the loss value and the classification accuracy of original image remain basically unchanged. So we propose IDIFGSM. Specifically, before we input the adversarial examples into the neural network, we will drop out the adversarial examples, that is, randomly set 0 for 10 pixels of adversarial examples, while dropout rate takes from 0 to 1. Our method can alleviate the overfitting of the adversarial examples in the substituted model. We further propose a gradient iteration attack method with multiple drop rate versions. In the single model attack setting, as a table, the results show that our method increases by 15.6% on average compared with IFGSM, and the DITI-IDMIFGSM increases by 15.4% on average than DITI-MIFGSM. In addition, our DITI-IDEMIFGSM achieves an average attack success rate of 79.70% on the 6 models, which is 21.4% higher than DITIMIFGSM. In the ensemble-based attack setting, as in table, our method combined with DITI-PIMIFGSM can increase by 1.4% on average on the denoise model. Our method combined with DITIMIFGSM can increase by 17.2% on average on the ensemble adversarial training model. Our method DITI-IDEMIFGSM can achieve an average attack success rate of 96.2% on the ensemble adversarial training model, which is higher than state-of-the-art gradient-based attacks. In addition, we extend the iteration times to 200 and find that DITIMIM can effectively prevent overfitting after adding our method. Let's conclude our work. We rethink the relationship between step size, iteration time, and maximum disturbance, and propose a new gradient iteration framework. In this framework, we can improve the attack performance of DITIMIFGSM easily. We verify that dropout has input invariance and propose IDIFGSM. Our framework can be well combined with our proposed input dropout method. We further propose a gradient iterative attack method with multiple drop rate versions, which can achieve 96.2% success rate in the defense model. If you have any questions, please contact the email. Thank you.